Alright, time for underdraftphysics.com, debatephysics.com. Also, but again, the debate is just underdeveloped. Let's just say, keep making efforts to contact. Why the hell is this thing open? I don't know. Anyway, just computers. Whatever. So comments. I'll do some really poor comments, but it's the only kind I get. But I'm continuing to try to find some, real physicist who wishes to, argue real physics, and understands some of it, actually. So this whole thermodynamic thing was a really interesting. I'm glad I did the video because I didn't really realize that heat isn't in the momentum universe for you people. You don't think heat has to be made out of momentum, like something has to sacrifice its momentum to cause something to be heated. That it can't just heat it for free. um, and certainly in all of these, like especially the ballistic pendulum, I wasn't really realizing that, theoretically, you don't think bullets have this energy in the sense that you can never collect it. So you can only collect it as waste energy. You can never collect the extra energy as anything useful. So the point would be is that the bullet could have 20,000 joules, and the gun recoil has two. It's more like 2002. So okay, 1,000 times has 1,000 times more energy. Okay. But the fact is that all I can collect is the momentum, and the ballistic pendulum proves it. And the math proves it, in the sense that the math doesn't allow it any other way. I can't collect more momentum, so I'm stuck collecting the minimum amount of momentum, which means 99% of the energy can't be converted into momentum, so it can't be converted into anything useful. And so it's always waste energy. So in all of these examples, there's no way to ever collect what you're calling this kinetic energy thing, because you can never convert it into momentum. You can only convert it into heat. And it has to stay heat, because you can't make the heat into momentum. Frankly. Oh, I mean, you could try. And if you did, you'd find that, there isn't much momentum there. So anyway, just didn't realize that that's what it's really about. You just don't understand that heat, the little motion of little things, little atoms, is caused by the motion of something else. And that the motion has to be used to cause motion. You can't make motion without using something's motion. Alright, so Piro says, according to you, the 10-ton boulder sitting on the ground for 10 seconds is generating the same amount of energy as it would if it fell for 10 seconds. Yes. Yeah, it's true. Where is that energy going? Well, obviously in both cases, the energy eventually will go into the ground. So in one case, it's constantly pushing on the ground for 10 seconds. In the other case, for a split second, it crashes into the ground and produces all of its energy. So in one case, let's say the energy was 500 watts. In one case, the 500 watts are spread over 10 seconds. In the other case, the 500 watts happens in, half a second, a millisecond, 1,000th of a second. All right, where is that energy going? Why isn't the boulder hot where it touches the ground? Well, the fact is it probably is. So it depends on how big the boulder is, right? Because we know that crushing pressure will create heat. You just didn't measure it, right? But besides that, it's obviously being dissipated into the ground. The ground absorbs it, pushes back, just like it does with us. There's nothing to see here, in the sense that this is just an argument about over how much time you dispose of energy. And the simple argument is that obviously if you take 5,000 watts or 10,000 watts and you spread over an hour, you wouldn't see much happening. But if I take that 10,000 watts and I make it happen in a second, you'll see white hot stuff happen. So yeah, it's just over how much time you're distributing the energy. And if you distribute energy over shorter and shorter periods of time, most of the things that we are familiar with can't handle that. That is, they can't move the energy through themselves fast enough. Now, if the speed of sound is connected to the speed of motion in objects. So stuff like steel have to move, they kind of move at a slow speed. That is, they transfer the energy through them even thermally, rather slowly. And obviously, if you're trying to push the energy very fast, it'll break that system. So sort of like a sound, breaking the sound barrier and causing a sonic boom, you'll break the system. All right. So yeah, this is not anything paradoxical or interesting in the sense that you're just basically asking me, I mean, if you were to put something that you valued, like your nuts, under the 10-pound boulder, a boulder, it's good, yeah, for 10 seconds, you're going to be counting those seconds going, holy shit, holy shit, holy shit. All those 10 seconds are going to be a problem. And yes, of course, if you save it all up and give you one big kick, it's also going to be bad news. But the fact is that the total energy, the energy needed to create those two things, is the same energy. Okay. All right. So this was way off. This is, I don't know, people are just too silly. Bin 6618, whatever that is. When the quanta collides with mass. So I've been over this so many times, right? I mean, so many times. You say it gives up momentum. Yeah, I say it sticks and pushes. Okay, in order for the mass to be affected. Well, there's different ways to be affected, right? I mean, if the mass is coming towards it, the energy reflects, and the thing loses a piece of energy because it reflects. So that's just a purely kinetic. 2 steel balls come in, 2 steel balls leave. So it's only in the circumstance where it's not moving or it's moving with it that it can add energy to it. But yes, something going very, very fast collides with something going pretty slow, and it pushes it. Not too challenging a concept. So the quanta loses speed. All right, so this is like saying if you were running and then I made you carry 50 pounds, you'd run slower. Yeah, duh. Okay, and then I let you drop the 50 pounds and now you're running fast again. I mean, not very challenging. Okay. But this is the way they want to play the game. It's all this little drivelly baby talk bullshit. So the quanta loses speed and then speeds up again to c. Yeah, the fact is the force bits carry a momentum that is perpetual. They can't have any less momentum. They're always pushing or always flying. There's nothing else they can do. That's just a condition of the universe, okay? I didn't invent it. The universe invented it. Photons do it. All kinds of things do it. All right. When the back to C, when the interaction with the mass is over, how would you know this? Because the simulation works perfectly. That is, with just these simple little rules, 2 + 2 + 3 physics, it perfectly duplicates charge. Something your physics hasn't come close to having any explanation whatsoever. Nothing. No mechanical explanation for why electrons and protons attract and electrons and repel electrons and protons repel protons. Nothing. Nothing close to a model of why that happens. Nothing. And you type this puke, this snarky puke. I mean, it's just so pathetic that you show them a simulation, you show them these simple things working, and they sit there and pretend it's not working. Yeah, no, it's working. It's doing exactly what Maxwell drew. That's an accomplishment, asswipe. All right, and you're just a petty loser. Oh, fuck. Cool t-shirt. Yes, I am a much snappier dresser, lately. Doesn't the lever tell us that the force times distance is the same on both sides? Again, you want to play the game. You have to account for what the thing does. Okay, and we know in gravity, 4 times the distance is only twice the velocity. And we know on the lever, twice the distance is twice the velocity, because the energy is being created in 2 completely different ways. One of them is, let's see how to state it. Well, it doesn't need a statement. It just means that you really do have to account for the fact that it's about the momentum of the object, the mv. Even your mv squared is made out of mv. And you have to account for the fact that the mv's don't match in the 2 circumstances. In the gravitational circumstance and in the lever circumstance, the mv's don't match, the mv squareds. Okay. If not, why? Why? Because it's a time-dependent force, as I've gone over thousands of times now. And again, some of this stuff you can know fairly. I mean, it's not even complicated. Gravitational body, I'm going to fly by. All right, this is, this is gravity for 5th graders, right? I'm going to fly by the gravitational body. It's a simple calculation. How much time am I going to be pushed by a 9.8 meter, let's say, force? Let's say the average over this distance is 9.8 meters per second. It's per 1 second. 9.8 per every 1 second I'm in the field of gravity. That math perfectly explains how much you're going to get bent. Perfectly. It gets perfectly right answers. All right, and the same thing is true with something coming in. Your formula, mgh, doesn't work. Can't do this. If it's already moving, it can't do it. Can't do the equation. And I think you're smart enough to know that yes, the faster you go into the gravity, the faster you're coming towards Earth, the less the Earth is going to give you in terms of increased velocity, because you're not going to be in the Earth's gravity long enough to increase your velocity. It's just not going to happen. And the same is true leaving Earth. The faster you leave, the less work you have to do against the gravity. I mean, come on, this is just ridiculous. Okay, the 1 mass lifts 4 mass 1 distance. The 1 mass lifts a 4 mass 1 distance, and the 4 mass lifts a 1 mass 4 distances. Okay, yes, we know the amount of distance, but we know that in that distance the velocity is 4 times. We know the mass is moving 4 times the velocity. So it's not the same, is it? So you're just going to ignore the fact that everybody knows it's not the same velocity, that 4 times the height only gets you 2 seconds of gravity, and you're only going twice the speed. And in this example, you're going 4 times the speed. And those two don't match. And that's the argument. It's not the same. Okay. It's the same amount of work in conventional physics. I'm saying that's absolutely a lie. Okay, you have no physical evidence. You have no experimental evidence that that's true at all. All right, and it's a simple fact of the momentums don't match. It's clear the momentums don't match. It doesn't matter rotational, it doesn't matter. The momentums don't match. You haven't even conserved the momentum, let alone start conserving something else. So you're comparing an apple and an orange, clearly, and pretending gravity is the same thing, same rules apply, and obviously it's not the same rules. All right. I mean, so this is their gimmick. Instead of dealing with the fact that they've never done any of these experiments, their physics, never measured anything. Okay. So, I mean, it's the first thermodynamic video, there's a little section where I just talk about the lever. And in the third one, there's a whole section where I go through the bowling ball, the lever, all the examples of how this freaking idiotic formula fails dismally, okay, to get anything close to a right answer. And so I will extract a link to that time code. And this is their lame response to losing 99% of the kinetic energy, being required to lose it. Yeah, in the case of the ballistic pendulum. Having no way to collect it ever. Fact. As anything useful, like momentum. Alright. Let's see. I don't know what this, seriously improving the quality of your videos. Yeah, well, whatever. He wants me to make show videos. Woo, 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 woo. Yeah. Not going to happen. Alright, so maybe that's all the video there is. I'll pause, but yeah, I don't. These are such shitty arguments. So again, like I said, I'm trying to contact some more physicists and see if I can get somebody who can actually make a reasoned counter argument, something reasonable, not garbage. All right, I'm back pretty quickly. I just thought, just the 25 times the fuel to go 5 times as fast thing. The idea that somehow their physics says you must use 25 times the energy to spin something 5 times as fast. The very fact that they say that's what the physics demands, and all of these assholes, none of these jackass commenters think that's true. They know that their car doesn't use 25 times the fuel when it's going 50 miles an hour than when it's going 10. They know that's not true. So why this pretending, that somehow you think the physics is perfectly right? And again, those numbers just get worse and worse the higher you go, right? So 10 times an increase in your velocity takes 100 times of the fuel. 100. Yeah. I mean, it just gets crazier and crazier. And we're right back to the bullet gun and Newton's third law, right? You say there's a third law, equal and opposite. I mean, this has been stated so many times in grammar school all over the place, this equal opposite. You don't believe in it, right? You don't think the gun recoil has the same energy as the bullet. I mean, it's ridiculous that you preach this crap and you don't believe it. But do you really, I mean, you can't realistically understand that if I could make an ideal lever, that there'd be no problem. Recoil of the gun over here, speeding bullet over here. Even football, come on, American football. You really think that 2 little guys going twice the speed, is 4 times the energy, or twice the energy of one big guy going half the speed? I mean, even the analogy of the 10-ton train going 5 and the 5-ton train going 10. I mean, you can know that the tug of war is not going to be won by the 5-ton train going 10. It's not going to win. Those are the same thing. So this shouldn't even be an argument. I mean, it's just amazing that all these hundreds of years, these facts have been sitting there and they have evaded them. They have evaded the whole subject of testing this. It's just amazing, that they don't have a single piece of experimental evidence to show us twice the speed being 4 times the energy, let alone 5 times the speed being 25 times the energy. Just so bad. Right, kind of going back to Piro's comment. I mean, I've made these argument about, tipping points and resonance frequencies, and the fact that, I mean, you could just obviously understand that, this blue light, red light thing. If I take the same 3 baseballs, I'm going to throw 3 baseballs. You can really understand that if I throw them in 3 seconds, 1, 2, and then 3, that it's probabilistic, okay, that there's a probability, okay, I can do a certain amount of make something happen. But that there's more potential to do something if I could throw the 3. Yes, there's 3 seconds, but I throw all the baseballs in the first second. So the 3 baseballs are going to hit something, bang, 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 instead of bang, time to relax, I can take it easy, bang, okay, and then time to relax, I can take it easy, bang. So we know that that's a decisive argument for, like, if you wanted to move a rowboat, or if you wanted to make something go faster. Especially something that's in some sort of condition where it's tied to something, rubber bandish or something. That, yes, the quicker I hit it with the energy, the more likely I can break it free. The slower I hit it with the energy, the more time I take before I give it hunks of energy, the less chance I have of breaking it free. So, there's not more energy in blue light. It's that you're distributing the energy more quickly, okay, in a smaller and smaller amount of time. And it's that small amount of time, okay, that means you've taken something that before it can slow down, you've added more energy. So obviously the maximum speed you'll reach is higher because you've added the energy quickly. So you can even think of it that way, just throwing things into a little cart. So I throw them into the little cart. If I throw them slowly, I throw it, the first one in, it goes 10 velocity, and now it starts slowing down. And so when it's going 2 velocity still, I throw another one hits, and now it's going 12 velocity, but it's slowing down, right? And so now it's left going 4 velocity, and then I throw the third one. And so I get up to a total of 14 velocity, right? But if I throw them all very quickly, then it's first going 10, and it goes, let's say, down to only 8. And then I throw the second one, now it's going 18, right? And then it goes back down to 16, and I throw the third one, and now I'm going 26. So obviously I preserve a lot more of the velocity, a lot higher velocity, one way than another way. And again, it's just the tipping point. You have to add the energy when something's moving in the same direction. When it's moving against your direction, you can't add energy. So it's just that simple an argument, right? Something's wobbling, you're going to add energy. You have to hit it when it's going in the direction your energy's going. If it's going in the opposite direction, yeah, they're going to do this reflection thing. You're going to lose velocity. All right. Come on. It's so obvious that's the advantage the blue light has. The blue light doesn't have more energy. It has advantage. It has more advantage. And there's a big difference between energy and advantage. Okay. Anyway, so we'll call that enough of a video now. So, till the next time, boy, you people suck. And that's the only thing proven in all of this. The only thing that's absolutely been proven is that people suck. You suck at making arguments. You suck at being honest. You suck at being anything other than petty cowards.